So let's start the review. So this problem is an application of the work kinetic energy theorem. So the work done, the net work done on a system, okay, will be equals to the change in kinetic energy of the system. And the net work will be the sum of all the work done by the forces acting on that system, which is equals to the change in kinetic energy. And work is the force and times the displacement. So the force parallel to the displacement. Okay, so this is the case when the force is constant. So here, let's try to, so of course you want to pause the video. So we have an 80 kilogram tire. So it's a special fitness tire, I guess. And someone is pulling on that. The force here is 150 Newton. The angle here is 10 degrees. And you see here it was already moving, so it has some speed here to begin with. And it must be a net force. So the net force is positive, so toward the positive x, okay, because now it's being accelerated, so the final speed is larger than the initial speed. Okay, so that means the net force along the x has to be positive, okay? This is 10 degrees. And what else do we know? We know the displacement. So displacement again is a vector. So we're going to put here delta x equals 5 meters. Okay. Initial speed is 0.5 in magnitude. And here it's going to be 2. So there is an acceleration between here and there. And it says that you have friction. But the frictional force, it's going to be smaller than the force here along the x-axis, since you have an increase in speeds, but you do have kinetic friction. So if I apply this equation, I'm going to say that the change in kinetic energy will be equals to the work done by friction, okay, plus the work done by the driving force, right, by the pull, okay, which is equals to the work done by friction plus, so you have to find the x component of the force. You see the force here has two components, x component, that's the one that is parallel to the displacement, and you have the y component, which is perpendicular. So we want to find this here, this component, which is 150 cosine 10 times, so the displacement is 5. So that will be the work done. Okay, so the change in kinetic energy, so that will be 0.5 times the mass times the final speed is 2 square minus 0.5 square equals the work done by friction plus all this here. So we have 150, the force times cosine 10, so a little bit less than 150, times the displacement 5. Okay, so we can have 738 point, I don't know what, 61. So that will be in joule. So the work done by friction will be equals to, so you subtract this from there, right? So plus 0.5 times 80 times 2 square minus 0.5 square, and you get about minus 590 if you keep two significant figures joules. And if you don't find a negative number, that means something is wrong, because the work done by friction is always negative. Okay, so this one is to review power. So power is the energy, is the rate at which energy is consumed or delivered. So energy consumed or delivered, meaning energy in transfer. Energy in transfer will be the net work over the time elapsed. And I put here a bar, so it's the average power. And you can use the kinetic energy work theorem. The net work done on a system is also its change in kinetic energy. Okay, and here you have the time. Or you can say that the average power. So in that case, the force here, so he's pulling with a constant force. So the mass here, it's gonna accelerate. So the average power will be the force, and the force is constant, and it has to be parallel to the velocity. Okay, so the velocity is in this direction. Okay, and the velocity is going to change, right? So it's going to increase. So here I have to put the average speed. So it's a scalar. So this is the average speed, and that will be the force. So you see the mass M is going from initial velocity 0. It's going to accelerate. Okay, and the final velocity here in magnitude is going to be 6 meters per second. It's going through a displacement delta x, and the time elapsed is 3 seconds. And during that time, there is a force applied that stays same. And so that means there is also an acceleration, right? The acceleration and the force are proportional to each other. So A is constant, F is constant. So it's going to speed up. It's spinning up from here to this position there. So I can use this definition. So let's use that definition here. So let's find the average speed. So because the speed is increasing at a constant rate, so then I can say that it's going to be the initial plus the final divided by 2. So it's going to be 0 plus 6 divided by 2, which is 3 meters per second. Why? Because you see here, the velocity is going to increase at a constant rate, right? The slope here is the acceleration. So the average will be just the midpoint here between 0 and the final speed. Okay, so I can use that equation. That will be only true if the acceleration is constant. And then for the force, I can just say ma. Okay, so the force will be the mass, which is 65. Acceleration, the definition is the final speed. So final speed is 6 minus initial divided by the time elapsed is 3, which is 65 times 2, which is 130 Newton. So the average power will be 130 times 3, which is 390 watt. So that's number 1. Number 2, I can use this instead. So the average power will be the change in kinetic energy. So 0.5 times 65 times final speed is 6 square minus initial speed square over the time elapsed, which is 3. So 0.5 times 65 times 36 divided by 3, and you get 390 watts. It's quite energy delivered because remember 1 horsepower is 746 watt. So 390 watt. Okay, so you divide 390 by 746. So it's going to be about 0.5 horsepower. Okay. So this is also a classic, and for the exam you will have like something like this. So it has to do with equilibrium, when you have the sum of all the torque equals 0, and the sum of all the forces acting on the system here also has to be equals to 0. And the system is just the ladder here. Okay, so let's look at the forces acting on the ladder. So first of all, okay, you have the weight here. So I'm going to call that W1. Okay, that will be the weight. So because it's all homogeneous, we suppose that the weight is just at the center. And this is 4 meters long. And you have the weight of the guy, which is 100 pounds. It's a large force here, 100 pounds. So that will be the weight, just the magnitude. Let's just make it a tiny bit smaller. And then you have the normal force, right? So normal force always goes from the ground to the system, and it has to be perpendicular to the ground, because normal means perpendicular. So I'm going to call that N sub 2. So it doesn't slide. And the reason for that is that you have static friction. Okay? And until you reach the maximum static friction, then you will be fine, because then it goes to kinetic friction. Kinetic friction is not as strong, and you're going to slide. Here you have no friction, but you have a normal force here. So that will be N sub 1. It's in equilibrium. So let's do force. First, let's do the sum of the torque equals 0. So you can compute torque different ways. You can find that will be the force perpendicular to the lever times the distance, or you can say it's the lever arm times the force, or you can use the definition of cross product and say it's a magnitude, in magnitude, that's going to be R times F times the sine of the angle between R and F. So we already discussed that. To simplify things, I'm going to use this definition here. You're going to see why it's going to be easier. So the trick is to take the fulcrum here. So that way, I'm going to get rid of N2 and the torque provided by N2 and the torque provided by the static friction. So in that case, this force wants to make rotation in this direction, so that will be counterclockwise. This one will also want to make it turn this way, and this one wants to make it turn that way. So in equilibrium, I'm going to say that the sum of the counterclockwise torque equals the sum of the clockwise torque, as discussed in class. Then I'm going to look at the components. So let's look at the component here. I'm going to use this definition of the torque. Okay. So that will be counterclockwise, counterclockwise. So I want to find the torque provided by this weight here. You see, it has a perpendicular component. So that will be W perpendicular, and it has a parallel one. So the parallel one is not helping, so I need to take this one. Okay, so that will be the torque. So here we have the torque provided by W2 plus the torque provided by W1 equals the torque provided by N1. So let's do a little bit of geometry. So this is 40 degrees. So that's going to be 40 degrees. Okay, if you make a nice drawing, you can see, but otherwise you see this is perpendicular to here, this is perpendicular to there. So that's going to be the angle, and that's going to be the angle. If you do the drawing nicely, you can see this is 40 degrees, and this is 40 degrees. So we're going to have the weight. So I don't need to convert anything because you have a equality here. So as long as I put my weight in pounds all over, then it will be fine. If it's feet, I can put all the distance in feet, and that will be fine. So the torque provided by the weight of the person will be 100 times cosine 40 times the distance between the fulcrum and the person here, which is 3. Okay, plus the weight. So here the same thing. It has two components, the parallel component here, which is W1 perpendicular, and this is the angle 40. So that's going to be 40 times the distance is 2. It's the distance is 2. So then the work done by, not the work done, the torque from N sub 1, it has two components. One component which is perpendicular, that's the one I want, it makes the rotation clockwise. And the one parallel, I don't care. So I need to find this one. So I need to find the angle. The smallest angle here will be this one, right? You can see that. Otherwise, you see this one is parallel to that. Okay, but if you if you draw it nicely, you see this is 40 degrees, this is 40 degrees. And of course, here you have a rectangle, so you want that. And that will be the opposite. So that will be a sine. So that will be N1 sine 40, and the distance is 4. Okay, so then you can do the computation. So it will be 100 cosine 40 times 3 plus 20 cosine 40 times 2, okay, divide by sine 40, okay, divide by 4, about 100. So the N sub 1 equals 100 Newton. Okay, I'm just, there is one significant figure, so I take 1. So it's about 1. Okay, but do not forget that I'm trying to find the static force here. So now I can use the sum of the forces equals 0. So that means whatever is pushing to the right equals whatever is pushing to the left. So you have N sub 1. That's the only force to the right. And Fs is the only force to the left. Okay, I don't have anything else because this is down, and this is up. So N2 equals W2 W1 1, but along the horizontal you have this. So the kinetic friction will be about 100 Newton. Now you can also say that up equals down. So in that case you have N2 equals W1 plus W2, which is 120 pounds. And I did a mistake here. That will be in pounds. 100 pounds, sorry. So this is also in pounds because everything else is in pounds. So unit is pounds for force. Okay. So this is coming from your book. It's a solved problem, but I just want to go over the methodology. So it's two gliders. So that means we are neglecting friction that gonna collide with each other. So it's conservation of momentum, total momentum before equals total momentum after. So this one has less mass. So this is before and after. We have B and we have A. So this is after. So what does it say? Velocity of B after is 2. So it means it's bouncing, it's reversing its direction. And this is plus, and this is minus, and I don't know which way it's going. Okay, so we can say that the total momentum before, so momentum of A plus momentum of B equals the total momentum after, so momentum of A prime plus momentum, I'm going to call that prime. So momentum of A after, momentum of B after, I'm going to call that prime. So before, we have the largest one moving to the right. But the smallest one is moving to the left. So I have to be very careful here that I have a -2 equals after B is moving to the right. So it's going to be a 0.3 times 2. And this one I do not know. I know the mass, and that will be the velocity after. So the total momentum after is, this is minus 0.61. 1 minus 0.6 is 0.4. And this is 0.6 plus 0.5 VA prime. So you can solve for VA prime. Or you can say, you see, this is the same momentum before. So here you need to get 0.4. So here that should be minus 0.2. So if you compute 0.2 divided by 0.5, you get 0.4. But there is a negative. So that means VA prime equals minus 0.4. So it has lost speed, right? Because it's moving back, but it's bouncing up. So to the right, and this one has moving up at 2 meters per second. Okay, so that will be the answer for the first question. Second question, the change in momentum. So the change in momentum for A equals the mass, so 0.5. The final speed is minus 0.4 minus initial speed is 2. So that will be 2.4 divided by 2, which is minus 1.2 kilogram meter per second. And change in momentum for B equals 0.3. The final speed is 2 minus initial speed is -2. I have to be careful here. So because that's going to be 4. So that's going to be also 1.2. So the momentum lost by A will be equals to the momentum gained by B, which we knew because that's called conservation of momentum. Whatever is lost by one equals to whatever is gained by the other one. So next question. How do we compare the speed, change in speed? So VA prime minus VA. So the final is minus 0.4 minus, that's for A, minus initial is 2, so minus 2.4. And for B, we're gonna have a final is 2, initial is minus 2. So that's going to be 4. So you see that the speed gained by B is larger than the speed gained by A because the mass of B is larger than the mass of A. So most of the momentum, in the case of A, most of the momentum goes to its mass. So here the momentum goes to its speed. You can think of that. So there is more acceleration for B than there is for A. Okay, but the change in momentum is the same and the force is the same. So this one is easy because it's just applying the definition. The gravitational force is going to be equals to the constant, mass 1, mass 2, and the distance between their centers. So G is very small. It's going to be 6. G is 6.67 times 10 to the negative 11. So just maybe a way to work on the scientific notation numbers. So anyway, robotic lander, so the weight is here. So if I take on Earth about 10, okay, I'm rounding out. So that means the mass here is 343 kilogram. Okay. And this is on Mars. So the force due to gravity on Mars, so the weight of this lander on Mars, it's going to be G, the mass of the lander, the mass of Mars, divided by the radius of Mars squared. Okay, so it's going to be 6.67 times 10 to the negative 11. And then you have the mass, which is 343. And then you have the mass of Mars, which is 6.42 times 10 to the 23. And here you have the radius squared. The radius is 3.4, so it's smaller than the Earth. Times 10, the Earth is about 6,000 kilometers. This is about half. 6 squared. Okay, so let's take all the number on one side, 6.67, and here you have 343, and here you have 6.43. Scientific notation, you have 23 minus 11, that's going to be 10 to the 12. And here, you're going to have 3.4 squared. Okay, I put the square here. and then square you have 10 to the 12. So you see it's convenient, you can cross this out, and all is left is to do the computation. So it's going to be 6.67 times 343 times 6.43 divided by 3.4 squared. And it's good about something like this. So I forgot where I am. Okay, 1270 Newton, about. It's gonna be about, right? 1270 Newton about. Okay, so that answers the first question. The acceleration due to gravity. So we have G prime over G. So that's the acceleration due to gravity for Mars, and this is the acceleration due to gravity for Earth. Okay, so what we can do is the force due to gravity on Mars equals mg prime, right? So this is on Mars. And on Earth, the force due to gravity, it's going to be the same mass g. That will be on Earth. Okay, and this is equals to 1272, and this is equals to 3430. So that means if you write the ratio between them, so G prime over G equals 1272 over 3430. That's going to be equals to G prime over, let's say it's about 10. Okay, so it's going to be equals to divided by 3430. So 30%. So on Earth, on Mars, you have 30%, 37% less weight than on Earth. Okay. So times 10. So G, the acceleration to gravity, due to gravity is 37% less. So about 3.7. So G prime is about 3.7 on Mars. So it's about 4. And on Earth, it's about 10. So that will be a difference of 37%. So here is a very easy and short problem here. So you have the Earth here. This is the radius. On Earth, the acceleration to gravity is about g. So g is about 10. And you have a satellite at about a distance 4 times the radius. So 1, 2, 3, 4. So this is a GPS here. And it's in orbit around the Earth. And the question is, what's going to be G prime? So you can do that using inverse square law, or you can do it algebraically. So you know that G, okay, it's going to be the constant here, the mass of the Earth, and the radius square. G prime will be G, it's the same Earth, but now the distance is 4 times R, everything square. So that's going to be GM 16R squared. So if you take the ratio between them, G prime over G, okay, it's going to be GM 16R squared. You divide, so you multiply by the reciprocal, GM, bye. So it's going to be 1/16. So G prime will be G divided by 16. So if you stand there at this distance here, the force due to gravity pulling on you, okay, compared to here. This here will be 1/16 of the weight. Now, if you are in a space station, you will be feeling weightless, but you still have weight. So let's do the next one. So this one comes from your textbook, University Physics. So it's at the end of the chapter, but we already discussed in class those examples here. So this is in Japan, and you have a Cosmo Clock 21 Ferris wheel, and it takes like you have 60 arms here, 60 arms, and it takes 60 seconds for one revolution. So it's like a clock. It works like a clock. Right? So to go from here to there, it takes 1 second. So one revolution is in 60 seconds. And so find the speed. Okay, so the speed will be distance over time. The distance is 2 pi r. The time is 60. And it says here diameter. So across here, 60 meters, no, 100 meters. So the radius is 50. So the speed will be 2 pi 50 over 60. So what you get, that's going to give you 5.24 meter per second. Okay, next question. So you have a passenger, and the true weight is 882 Newton, 882 Newton. So the mass is about 88 kilograms. That's the true weight. And remember, the weight is always given by the normal force. So you have mg, that's going to be the normal force. So normal force is going to give you the weight, because it's going to tell you how hard you are pushing on the bathroom scale. So now the wheel is working, and here, what's going to happen at the highest point? So now the passenger here is here. Okay. That's the passenger here. Let's give it a head, and it has a velocity v here, 5.24 meter per second. So there is a rotation. Let's say the rotation is this way. So remember, each time you have a circular motion, you need to have a centripetal force, so a centripetal acceleration toward the center. Otherwise, off tangent, it will go. And what is down in that case? In that case, it's going to be the weight. See, the force are the weight, mg, and mg has to be larger than the force up. And what is up? In that case, that will be the normal force, because the normal force always goes from the contact here, surface contact surface, and the system. So here we have a normal force. So the free body diagram will be a weight down, the normal force up. And this here has to be larger than that one. Okay? You need to have enough force pushing the person down so it doesn't go off track. So we always take toward the center to be positive as a direction. So the acceleration will be in this direction. So now we can use Newton's second law. So this is positive, so mg minus the normal force equals mv squared over r. And you want to find the apparent weight. So imagine you are on this wheel here, you're going to feel lighter, right? And here you're going to feel heavier. So let's find the normal force. It's always the apparent weight, or the weight is always given by the normal force. So that's going to be m, and here you have g minus v squared over r. So the mass in that case is about 88.2. That's going to be 10 minus 5.24 squared over 50. And you get about 834 Newton. So the person will be lighter. Okay, so that will be, this is the apparent weight. Okay, so if you do 882, the true weight minus the apparent divided by the true one, we get about 5%. So the person will feel 5% lighter. So now when the person is here, so this is the person here sitting there, and doom doom. So what's gonna happen? You still need the weight. The normal force, sorry, is always toward the center, right? That will be your normal force, and the weight will be in this direction. But now you see that this free body diagram normal force is larger, the weight is small. And you're gonna feel heavier, when you go, you're gonna feel heavier. So by how much? So use Newton's second law. Always toward the center, always take the direction to be positive. Okay, because that would be also the direction of the centripetal acceleration. So then we're gonna have that positive n minus mg equals mv squared over r. So the apparent weight will be g plus v squared over r. So that means that your weight has increased by a factor mv squared over r. So your new weight will be, if you plug it in, it's about 930 Newton. So it will feel 5% heavier. So the issue with those wheels is that, let's say you are sitting here, if the wheel goes too fast, off tangent you go. So in that case, normal force will be equals to 0. So as it's going to move faster and faster and faster, if you look at the equation here, when you go faster, 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 you're going to move, you're going to feel lighter and lighter and lighter. But this cannot be over g. Okay, so that means the limit is g equals v squared over r. So the limit will be the square root of gr, right? And that will be square root of 10 times 50, which is 22. So if you go beyond that speed here, off you go, right? But I suppose that you have a seat belt, but still it becomes dangerous, and it will spin too fast. So if this is the speed here, you can always find how long it will take to go around. That will be 10 seconds, right? That you're gonna feel very sick. So this one we already reviewed that in class, but it's about impulse. Okay, so the impulse is a vector. So you can use two definition. Two definition, it's going to be the average force. Okay, so that will be the net force times the time the impact lasts. Or we can say it's also equals to the change in momentum. So, okay, let's do a drawing. So it's arriving to the left. So this is the left. So here you have 0.4 kilogram and the velocity is to the left. So I'm going to write the magnitude here. So it's 30. And then I have to decide which way is plus, which way is minus. So I'm going to take plus to the left and minus to the right. So it's going to bounce off and it's losing some energy because now it's coming back with 20 meter per second. So they want you to find the impulse. So it's on one dimension, so I don't worry about this arrow. So it's going to be the change in momentum. So it's the mass, the final speed minus initial speed. Okay, but I have to be careful with the direction. So the final speed, so this is the mass, final speed is negative. So it's going to be negative 20 minus initial speed is 30. Okay, so it's important because otherwise you're going to subtract. And you don't want that because it takes a lot of force to make something bounce off compared to just stop it. So the impulse will be 0.4 times minus 50. So it's going to be 220 minus 20 Newton per second. So that will be the impulse. And then they want you to find so it's like a kick. The time of impact is hundredths of a second. And you can apply the equation average force times the time of impact equals the impulse. So that means your average force equals the impulse divided by the time elapsed. So it's going to be 2. So it's going to be negative 200 Newton. So that's a lot because that means if you have a bathroom scale here, you're going to read, so it will be 200 kilo about, and 200 kilo is about 400 pounds, right? So you see the kick is huge and the kick is negative. So it means it's going to be to the right. If you find to the left, that means there's a mistake, right? Because the force exerted by the wall is to the right. So this one is about equilibrium and torques, and it's from your book, textbook, University Physics, and it's solve problem 11.2, but I thought it was interesting because it's very much like a problem like someone is doing the plank. So you see, let's say the center of mass is somewhere there. So you're going to have the weight here. And then that will be the weight. And you see that from here you have a normal force. Maybe it has to balance the weight. So you have the balance force, the normal force here, and sub 1. And you have a balance force here, and 2. So you see that normal force here, you can put a bathroom scale and you will have some reading there. And you can put the bathroom scale and you have some reading here. And what you can see is that here it will support maybe 60% of your weight, and here it will support about 40% of your weight, right? So it's in equilibrium, which means that up, so N1 plus N2 equals W, and then relative to a fulcrum, the axis of rotation, you can take it here, you can take it there, or you can take it there. So let's say if I take my axis of rotation here, that will be x2 and that will be x1. So then you're going to have x2 times n2 will be equals to x1 times n1. And that actually is going to give you here, that distance here is the center of mass. So using here, you can find the center of mass using that equation. So here it's the same idea, except it's a car. And so it's a car. So let's say this is the front, this is the rear. So someone is sitting in the car. And so it says that here, the normal force on the front, so you have more weight on the front than you have in the rear. So it means, so this is the ground here. Which means that that force here will be about 0.53 times the weight. So 53% of the weight is pushing on the ground. So the ground push back. So normal force. So that if you put a vacuum scale, you will read 50% of the weight. And here you have also here I'm going to call that N sub 1, and here I'm going to call that N sub 2. So you're going to have more weight here than you have there. So that will be 0.47 times the weight. So the center of mass should be not in the middle, but rather like towards here, right? So actually that will be 53% of the distance between the axles, and that will be 47% of the distance, but we can show that. So anyway, so that's going to be the weight. And so they call that distance here. So the distance here, the total distance here is 2.46 meters. And the distance here is x. That's what I want to find. And that will be the center of mass, right? That's the center of mass. So you can already see that distance here will be 53% of that. But let's show that. So first we decide of a fulcrum. You can put your fulcrum here, you can put the fulcrum here, you can put the fulcrum there. We'll get the same thing. I'm going to take it here. Okay, so if I take my fulcrum here, this here wants to make a clockwise torque, and this one wants to make a counterclockwise torque. So in equilibrium, the sum of the clockwise torque equals the sum of the clockwise torque. So clockwise, that's going to be here. So it's going to be N2, which is 0.53 times the weight times the distance to the fulcrum. That's going to be 2.46 equals clockwise. It's going to be this one. So it's going to be just the weight times x. Okay, I'm going to call that x here. And you can solve for x. So you see, x will be 53% of 246. And you get about 1.3 meters. And it's also the location of the center of mass. So you can do that experiment here, put a bathroom scale here and put a bathroom scale here, and you will see the repartition of the weight. So for the test, I will give you the work done as a function of time by a force on a system to find the power at a given time. So it's called the instantaneous power. You will have to take the derivative. So this one, it's not exactly the same, but I'm going to go over it and then I will discuss what's going to be on the final. So this is also coming from university physics. So you have two definitions for power. You can use this definition. Okay, so it's the rate at which energy is transferred, or you can also use the equation. It's going to be the force times the velocity. So if it's an instantaneous power, that will be the force at the time. So let's say at t equals 5 seconds. So it's going to be the force at t equals 5 times the velocity at t equals 5. So it's not the same as, for example, sometimes we talk about the average power and the force is constant. So then you will do the force times the average speed. In that case, it's not the same because here we are talking about instantaneous at a given time. So if I use that definition, it's much, much easier. So let's look what's going on. So you have a crate here and someone is pushing. So energy is being transferred from the person to the crate. So that will be work done on the crate. So at t equals 0, there is no speed. And it's gonna speed up here, boom, boom, boom. And it's gonna have a speed. So here we want to find out t equals 5 seconds. So it's gonna speed up. And the force is increasing with time. So he or she is pushing harder. The acceleration is constant and it's going to be 2.8. Okay. So if I use this equation, this one, okay, so power will be as a function of time, the force, which is 5.4 t times the velocity. And you see the velocity increases by 2.8 every second. So after t seconds, the velocity will be 2.8 t. So then you can compute 5.4 times 2.8. It's going to be 15.12. So 15.12 times t squared. So the power at a given time, so t equals 5 seconds. So the power delivered at that time, it's going to be 15.2 times 25. 15. Why did I say? Oh, 15.12 times 25. That's going to be about 378 watts. Now, you can do a computation here, quite advanced, not advanced, but more complicated. And at some point, you're going to get that the work done at a given time, not the work done, the power at a given time, you're still going to find, no, if you take that path, you're going to find that will be like what you're going to have for the test. So the work done at a given time, it's going to be equals to 5.04, and you have a function of time. Okay, so you can show that. I can show you how to do it, but you can, if you go this path here, first you have to find the work as a function of time, and then you take the derivative. So if you take the derivative, okay, you take the derivative of that, so it's going to be 3 times 5.04, and then here we have a t square. Okay, so that's going to be 15.12 times t square, and that's going to be the power at a given time. So at t equals 5, you're going to get the same thing, 15.12 times 5 square. It's going to be 378 watts. So to get to that, so that's going to be on the test, something like this. So it's not that hard. You just take the derivative. What might be more complicated is how to get there. Okay, so because you need to find the work, and the work done is you have to take the force, and you have to take the derivative over the distance, right? Because that's a definition of work. So the work done will be, and we do have the force as a function of time here, but dx, it's not great. So we want to get rid of the dx. So what we do, you divide by dt and you multiply by dt. So then it's going to be the integral of 5.4t times, and then you have the velocity, which is 2.8 t, and then dt. So you take the derivative of that, and you're going to get to here. So it takes more steps. So that will be the question on the final. Just something like this. So I want to go over this one. So this one is from your textbook at the end of the chapter 11. And so it will be like the one you're gonna have for the exam, except this one is a little bit challenging. So it comes from the textbook University Physics, and it's a typical problem. And the thing here is that they give you TMI, too much information that you are not going to use in the problem. So first you want to read over. So you see here you have a cable. So already you can see that you're going to have like you're going to have a tension, obviously, here. Okay, so you're going to have a tension here along the cable. That's going to be a tension. I can call it T sub 3. Let's see what else is given to me. It's going to be the angle, I think, is given somewhere. I'm going to call the angle here alpha. Maybe the angle you have to find. Okay, what else is given? So the sine, the beam. Okay, so they give you the length here. So the length from here to there, it's going to be 2 meters. Okay. So what else? And it has a mass of 16 kilograms. The uniform horizontal is, no, just kidding, 2 meters. I don't know why did I say 2 meters? It's the cable, which is 2 meters. So you see the first step you want to do is report all the information. So this is not 2 meters, it's going to be 1.5 meters. 1.5 meters, okay? And then the 2 meters is the cable. So this cable is 2 meters. So already we can find alpha, right? So we can say that cosine alpha equals 1.5 over 2. So that will be our first step. It's already something. We can find the angle. Okay, so it's going to be 1.5 divided by 2. It's going to be 41.4. Okay, so I have this alpha here. This is 2 meters. And then what the mass of the uniform beam supporting the center has a mass. So 16 kilogram, it's going to be the beam. Okay, so the mass of the beam is 16 kilogram and the length of the beam is 1.5 meters. Okay, so the center of mass relative to here, the center of mass will be somewhere at the center at 0.75 meters, right? Okay, and then you have the sine, and this one has a mass of 28 kilogram. So the mass of the sine is 28 kilogram. Okay, and the length is 1.2 meters, but this is TMI. That means we are not going to use this information because the string here is what matters. Okay, here it's going to pull on the beam. This one is going to pull on the beam, and really, we do not care how long is the beam. So that will be TMI. And then the two wires are each 32 centimeters. So this is also TMI. Okay, we don't care how long are the wires because the tension is always transmitted through the wire. Doesn't matter how long they are. So this is just to confuse you. This unit, okay, so it means between here and there, okay, that's going to be 0.9 meters. So how much is left? It's going to be 0.6. So that distance here is going to be 0.6, okay, because 1.5, yes, 1.5 minus 0.9 is 0.6. So if this is 0.6, you see that the center of mass is going to be somewhere here. Okay, so that will be your center of mass. So the center of mass, okay, it's going to be at the center, right, of the beam. So the beam is 1.5 meters. So here, I'm going to have the center of mass. That's going to be 0.75. That's going to be 0.75. So here, you have the center of mass. Okay, so the first step is always to understand what's going on. So you have the center of mass, and this is alpha, and here that's 0.9, that's alpha, and here you have your center of mass. Okay, so they want to find the tension, okay, the minimum tension, because if it's not that minimum here, it will break. Okay, and it's in equilibrium. Okay, so let's make another drawing. Let's look at the forces acting on that side. So you're going to have the tension here from the cable. The system, always look at the system. Okay, so that's going to be the system I'm looking at. Okay, so it's acted upon by T3. You have a tension here pulling down. That's going to call that T1 or T2. I'm going to call that T1, okay? And they are equally, so if the center of mass is here, you see they are the same distance, okay? But anyway, that will be T1 and T2, and we have the center of mass. And the sign here is larger, okay? So here we have the weight, that's going to be the weight of the beam. I know how I'm going to call that W. Okay. And then here you have a hinge. So what's going to happen? This is pushing on the wall. So the wall is going to push back on it. So we can call that a normal force. Okay, so it wants to slide here, and the hinge is, you have this force here, right? So the beam wants to push the things down. So you have this static friction that will prevent the beam from sliding. If it was made of ice, for example, it could slide. So sometimes it's called a reaction force. Okay. So it's hard to see anything. So let's do a drawing again. So you have the wall, you have the beam here. Okay. And then you have the tension, you have the cable here, and you have T2 here, and then you have T1 here. You have the center of mass somewhere here because this is 0.6. So so that will be 0.7. You have the weight here, which is 66. Okay. And what else? You have a force from the wall, and the components will be a vertical force, which is like a static force, and you have a normal force this way. And you have T3 that way. Okay. And then you have all the distance. So this is alpha. So that's going to be from here to there. We have 0.6. From here to there, we have 0.75. And the whole thing here is 1.5 meters. So I don't have any space left to do my computation, but it's fine. The other thing, when you have a sign, so this is your sign here, and this is 28 kilogram. So the weight here is 280, and you have a T1 here and a T2 there. Okay, T1 and T2. So you see that they're going to be equal to each other, and they share the weight. So T2 here will be, so down equals up. So T2 will be 140, and that will be 140. And we take G equals 10. So we have this, we have that, we have that. We want to find this. And we're going to say that the sum of the clockwise torque equals the sum of the counterclockwise torque. So I'm going to take the fulcrum here. So I get rid of those forces here. So that will be N. So that will want to make, what is it? Counterclockwise. That will be counterclockwise. That will be counterclockwise. And that will be, this way. Okay? This one will want to make a clockwise. Okay. So T3, of course, has two components. Okay. It has a Y component here, and it has a X component. T3Y. That will be T3X. So the Y component, it's the one that is making that clockwise. Okay, so the sum of the clockwise torque will be provided by T3Y. Okay, because remember, torque equals one way. The torque about the fulcrum is the perpendicular component, perpendicular to the lever here, times the distance in magnitude. So T3Y is the Y component, and you see it's a sign. So it's going to be T3 sine, okay, because you see it's a rectangle here. So that component will be sine alpha times T3 equals, and then here you have T2, which is 140. So 140 times the distance here, which is 1.5 plus, and then you have the weight, which is 160. So 160 times the distance, which is 0.75, plus another 140. So 140, but it's not as efficient as this one because it's closer, so times 0.16. And the torque provided by this one and that one equals 0 because it's attached to the fulcrum. Okay. And I forgot something here. I forgot the distance. Distance here is 1.5. So here I should put 1.5 times 1.5. Okay, that's the equation that you need. Okay, I forgot to put my distance here. So T3 sine alpha, and then you have 1.5. Okay, because that will be F sine, in that case, times D. Okay, so that's the component perpendicular, but I forgot the distance. Okay, so now you can solve for T3. And so it's going to be 140, always the distance, because it's a term, plus 160 times 0.75, plus 140 times 0.6. Okay, you divide by 1.5, enter, you divide by sine 41.4. And you get about 417. So the magnitude here will be 417. It's in equilibrium. And then the vertical force. Okay, so you see the beam is trying to push down the hinge, so the hinge is pushing back up. So now I can say that the sum of up equals the sum of down. That will be easier than I could take the fulcrum here and do the computation again. It makes things more complicated. So instead I'm going to say up equals down. So up will be T3, and then up is again the sine, so it's going to be sine alpha equals down. You have the 140, okay, plus another 140 plus 280. Okay, and up, I forgot again, here, up will be also that force here. That's also up, that vertical force. And T3, we know it's, we already know, so it's 417. So this is 417 times sine 41.4. Okay, so now we can say that it's 140 times 2, okay, plus 280, okay, minus 417, and then you have a sine 41.4. I'm not sure. Let's see if I forgot something. So 140. Ah, no. See, 160 here. Sorry. The mass is 16 kilogram. So 160. So let's do that again. 140 and 140 is 280 plus 160. Okay. Minus 417 sine 41.4. Okay. one about 160. About 164. If you want to keep 1 to 3 significant value, and this is because I tried to simplify here, and I took this. Okay. So here you are just applying the equation, the rocket equation, and it's in your equation sheet, I think, and it's from your book, this one, University Physics again. And just to remind you how it works, let's say you have someone here, and on the wagon here there is no friction, and maybe this person has some potato here, so he's gonna throw potato forward. Okay, so the mass of the potato is dm, so it's a little bit of mass, and this one has a large mass, and he keeps throwing potato in this direction with a speed u. Okay, so that will be the ejection speed. Okay, and so as a reaction, of course, the wagon is going to move in this direction, so it's going to increase its velocity by delta v. And faster you're going to throw those little masses, faster the wagon is going to move backward. And more of it per unit second, of course, it's also going to move faster backward. So this is a conservation of momentum. Okay, so the momentum here, the change in momentum here will be dm times the ejection speed, because initial speed will be 0. Okay, so there is no speed, and the speed is u in that case. Okay, so it will mean change in momentum here of this mass here, P1 will be equals to the change in momentum of that platform here. That will be like the rocket, right? So it will be minus the mass. So this is like a rocket, and this is like a gas. And this is the gas, the little bit of gas being ejected. So it will be the mass here times delta V. So we get the equation, which is Tm, okay, times U equals minus M delta V. Okay, so that will be the little bit of mass being burned at that speed, and the rocket is going to change its speed by delta V, and at a given time it has a mass that will change with time. And this is a constant here. So that will be this. So I divide both sides by the time. I derive by the time both sides. That's going to be minus m delta v over delta t. So here you have mass times acceleration. So that's what we call the force. That force here is a reaction. For every action you have a reaction. So that will be the force that we are trying to find. So that will be what we call that. We call that the mass flow rate. So it means the rate at which the mass of the rocket is changing. The rate at which the mass of the rocket is decreasing as it's going to expel gas, right? So that will be the thrust. Okay. So we see that dm over dt, okay, it will be 0.05 kilogram per second. That's a rate. That's what we need. We need a rate. And we have U here, which is 1600 meter per second. So that's the speed relative to the rocket. What's going to be the thrust? All you have to do is to multiply. So the thrust, it's going to be 1600 times 0.05, and you get 90 Newton. So for every action, you have a reaction. So can you operate when there is no atmosphere? Yes, because you see, the rocket is pushing on the gas. When you have an airplane, it will be pushing on the atmosphere, on the air. But in that case, when you have a rocket, I don't know how to draw a rocket, but you see it's pushing on the gas. So the gas is pushing a big speed because you have a little bit of mass. So the gas is pushing back on the rocket here, and the speed will be very large. Okay, so the answer is yes. How can you steer it? So if the rocket goes in this direction, okay, so if you want to make it turn, okay, so you want to apply a force in this direction here, force. So you need to push the gas in that direction. So you need to push in a direction perpendicular to the trajectory. Could you brake it? Yes. If the rocket is going this way, you just have to, if you want that to brake, to slow down, you have to throw here in the same direction as delta V, and it's going to slow down. The speed is going to decrease, stop. And maybe reverse its, so this one is easy. It comes also from your textbook, end of chapter, problems. And you just need to have a drawing. So you have a swing. So you have the mass M, which is the 25 kilogram, and here it's 2.2 meters, the length. Now she's above here. So here 2.2, but she's at this level here. So, and then that will be the ground. And you can say potential energy here equals 0. And that will be the angle here. It's given 42 degrees. So they want to compare the potential energy here to there. So for that, you need to find the height here, h. So this is just geometry, because we're going to take this right angle triangle. So this is 42 degrees. And I'm going to call that length here, from here to there. I'm going to call that from here to there. I'm going to call that L1. And the whole length here is, from here to there, is 2.2. So I want to find this height, so I can find this, this length, so I can find that height here. So you see, you can use cosine will be equals to L1 over 2.2. So L1, if you do that, you get 1.63 meters. So it means that the height will be 2.2. So this minus that, minus 1.63. So you're going to get 0.57 meters. So 0.57 meters, about 50 centimeters or so. So the potential energy relative to the ground is going to be mgh. So it's going to be equals to the mass 25 times 10 times 0.57. And I take, just to simplify. So potential energy is going to be about 142.5 joule. So I don't know, let's say they want 1, 2, 3 significant value. So that's going to be about 143 joules. How fast it's moving. So in those situations when you have no friction, the equation for the speed is always 2gh, and you take the square root, okay? Or you can say potential energy is going to turn into kinetic energy, and you see the mass does not matter. So the velocity equals the square root of 2gh. So the speed here, right? So it's doing something like this. It's moving, and here it has some speed. Okay, red, so that will be the speed here. And it starts from 0. Okay, so I should say here, actually I should say that it's going to be the change in kinetic energy, and initial velocity equals 0. So that works if the initial velocity equals 0. So you turn potential energy into kinetic energy, initial velocity equals 0. Okay, so to make it clear here, I should have written that it's the change in potential energy, so mgh equals the change in kinetic energy, which is 0.5, the final speed squared minus initial speed squared. Okay, and if you do that, you get square root of 2 times 0.57 times 10. So final velocity is about 3.34 meter per second. So what's the work done by tension? So you see here the tension is perpendicular here. So it's not changing the velocity. It doesn't make the thing go faster or slower. So the answer is there is no work. That's why you can apply conservation of energy. Okay, it doesn't take energy away because it cannot change the speed. Okay, it's totally perpendicular. So the tension is perpendicular to V. Okay, so it makes the thing turn, but it doesn't make it go faster or slower. So this one is not too hard, and you're gonna have something very similar to this. So you have the spring and the mass, and this is unstretched, so it's a resting position. And now you're gonna stretch the spring, so you are doing work on it, so it's gonna be stretched, okay, to a new position here. So that was the resting position. Now it's going to be at 0.1 meters. So all the work that you did is going into kinetic energy, elastic kinetic energy. Okay. And then you're going to let go. So all that energy, okay, is going to turn into kinetic energy, but not only. It's going to go also into heat. So when it's going to go through, so it's not stopping here, it's going to keep going. So it has a velocity v. Okay. So all that potential energy goes into kinetic energy, but on its way, you see the frictional force here is acting. Okay. And some of the energy is going to be lost into heat. And you also have the mass here, the normal force here, and you have the restoring force here. Okay, so let's write kinetic energy. Let's write conservation of energy. So before you release, everything was in kinetic potential, elastic potential energy. Some of it, so that will be energy in. But some of it is lost to friction. So that will be the heat, right? So that will be the work done by kinetic friction. So some of it is lost to heat. So whatever is left at the end is going to go to kinetic energy. Okay. And we have as a second equation, the kinetic friction equals the coefficient times the normal force. And we have as a third equation that the mass mg equals the normal force. So those two equations is going to give us that the kinetic friction equals uk times mg. So whatever we begin with, which is 0.5 times k, is 50 times the stretch 0.1 squared minus the energy lost to friction. So that will be the force, which is 0.25 times the mass, which is 0.5 times g. Okay, you see 500 gram is 0.5 kilogram and g is 10. Okay, so 0.5, 0.25, so that's g times the displacement, okay, because this is work, equals 0.5 times the mass times the speed squared. We can try to simplify a tiny bit here, and this gonna be 1. 10 times 0.1 is 1. So we have 50 times 0.1 squared minus 0.25 equals 0.5, yes, 0.5 v squared. And you get 50 times 0.1 squared minus 0.25. Okay, and you divide by 0.5, and you get 0.5. I didn't find that. Did I square it here? Minus 0.5. Yes, so just making sure 0.1 square, so that means you divide by 100, you take away 0.25, and you divide by 0.5, alright, and you take the square root. I take the square root, sorry. Which is 0.7. So v squared equals 0.5. So v equals 0.7 something. 0.7. V1. Okay. So this one is a recoil situation. So recoil meaning at the beginning, nothing is moving and you have a rifle here. So I'm going to call that number 1. Okay. So at the beginning, the bullet is inside and after the bullet is moving this way with a very large speed. So that will be the thing number 2. This is thing number 1. And there is a recoil here. So I'm going to call that V1 and that's going to be V2. That's going to be M1 and that's going to be M2. So it's the same situation with the ice skater, right? So have M1 and M2. So this is also a recoil situation depending on the mass, the speed. If this one has less mass, the speed will be larger and the speed here will be smaller. But in a recoil situation, I always have, because of conservation of momentum, M1 over M2 equals minus V2 over V1. So in that case, velocity is a vector. So one direction will be positive, the other direction will be negative. That's because the momentum before equals 0. So because they are not moving, so the momentum after is also equals 0. So we have M1 V1 plus M2 V2. So that's after equals 0. Momentum is conserved. Okay, all the forces acting could be inside the system, but the system is isolated. Okay, so now it's easy. We see that the mass of the bullet here, the mass of the rifle is 3 kilograms. And then the mass of the bullet here will be 0.005123 kilogram. 123 kilogram. The speed relative to the ground is 300 meter per second. And we want to have V sub 1. So I just do M1 over M2 equals minus V2 over V1. So we have 3 over 0.005 equals minus 300 over V2. So you cross multiply divide, so 300 times 0.005 over 3. So it's going to be 0.5 meter per second. Negative meaning that if this is going to the right, this one will be moving to the left. It's a vector. So what's the final momentum? So each of the one, if each one will have the same momentum, right? So for example, if I take the rifle, I'm going to have the mass times, so the mass is 3 kilograms times the speed is 0.5. So the momentum will be minus 1.5 kilogram meter per second. The momentum for the bullet, it's going to be 300 times 0.005 and you get 1.5 kilogram meter per second. So the momentum will be the same because you have conservation of momentum. What about the kinetic energy? So kinetic energy will be something else. So kinetic energy for 1, it's going to be 0.5, the mass. But you see here, a lot of kinetic energy is going into the speed. And the speed is, that will be 2. Did I mess up with between 2 and 1? So you will figure this out. That was number 2, that was number 1. That's supposed to be 1 here. Okay. So the speed is 0.5 squared. So kinetic energy for the heavy object is 0.375 joule. So kinetic energy for the bullet, 0.5. It has a small mass, but it has a huge speed, and then the speed is squared. So the kinetic energy, if you do the math, it's going to be 225 joules. So it means the kinetic energy is more for the bullet than for the rifle, because you see, it has moved a larger distance, so more work was done on it. So you start with the energy in the powder here, and that more of it will go to the bullet than it will go to the rifle. So kinetic energy here is larger. So this one has 2 parts. The first part is easy. So you will have something similar for the exam. And the second part comes from the book, and it's a bit more challenging. So here you have, so in the first part, you know M2, which is 10 kilogram, and you know M1, and you want to know the acceleration, right? So you suppose it's going to go this way, it's going to move that way, okay? And here you suppose there is no friction. So it's a typical problem. So I'm not going to go into details because we discussed that in class, but you can think of this like a bag. Okay, you put everything in the bag, and the bag is actually accelerating in this direction. Okay. So the driving force, what makes the bag falls, it's going to be the weight of M to G, and what is slowing it down will be the components of the weight here along the inclined plane. And I told you, with the inclined plane, the weight straight down has 2 components. One component is M1G cosine, and one component is M1G sine. And M1G sine is always along the inclined plane. Okay, so in that case, it doesn't help the motion, it's opposing the motion. But the force here is M1G sine, always, 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 always. Then it's easy because you see, you're going to use Newton's second law. So the net force equals the mass times the acceleration. So the net force will be the driving force of M2G minus whatever is opposing the motion. So that will be M1G sine alpha. The total mass is M1 plus M2, and you have the acceleration. See? So the acceleration will be, so M2 minus M1 sine alpha, and then here you have G, so you can factor out the G over M1 plus M2. You see here that if M2 is very, very large, okay, so that means that acceleration will be G, which is not the case here. So the acceleration will be mass 2, which is 10, minus 10. sine 53.1 and then times 10. So you can factor out the 10 over 20. Or you can just simplify it here. Okay, and what you get, let's see if you can factor out the 10. So 1 minus sine 53.1, okay, times 10, okay, divided by 2, okay, so it's gonna be about 1. Now, if we take the same problem here, so that comes from your book. So in that case, it's a little bit more challenging. It's more challenging because it's going into several steps. So it's just if you are interested. So I'm not going to solve everything. So first, what is given to you? You still have 53.1. Okay, but now you have friction, so there is friction here. The coefficient of friction is 0.4. Mass M2, you do not know. And do we have the mass 1? So this is 20 kilogram. Okay, and it descends when delta y is 12 meters. So I'm going to take down to be positive, because I like to have the acceleration to be positive. So the displacement is 12 meters. And the time elapsed is 3 seconds. So it's before it hits the ground. So step one, we need to find the acceleration using kinematics. And we are missing one more information. Initial speed is 0. So we can use the first equation of kinematics. So displacement equals 0.5 times the acceleration t squared. So if you do that, that's going to be 12. So 12 equals 0.5 acceleration times 3 squared. And you find that, do it yourself, the acceleration is 2.67 meter per second. Because you have to pause the video each time. So 1, 2, 3, I keep 3 significant values. So that was 12. Okay, so step 2, you apply the same principle. So it means everything is in the bag here. You're going to have the driving force pulling down. So that will be M to G. You still have here mg sine. So m1 g sine opposing the motion. You also have the frictional force also opposing the motion. And you have the kinetic friction equals the coefficient times the normal force. And remember, with inclined plane, the normal force is always equals to mg cosine. So you have the frictional force equals mu k mg cosine. And this is a 1. So we can find. You don't have to do it algebraically. You can go straight to the numbers and plug in here. So anyway, I just show you the idea. So the driving force is m to g minus, it's opposing the motion here, so it's going to be mu k times the kinetic friction, so m1g cosine alpha, so that's the normal force, minus I also have this m1g sine, that's going to be equals to like before, M1 plus M2 times A. And the idea is to solve for M1. So 0.20 G, so M2G, so M2G, M2. Okay, so it's going to be, I'm looking for M2 or M1. I'm looking for M2. So M2. M1 I do not know. So I'm looking for M2. M1 I do know. So M1 equals 20 kilogram. So we have M2 I do not know. So M2 G minus, this is 0.4 times 20 times 10 times cosine 53.1 minus M1 is 20 times 10 times the sine 53.1 equals, so here I have a M1 which is 20 plus M2 times 2.67. Okay, so this is just an equation and you need to solve for M2. Right, so you just have to solve for that. And so M2, factor out here 10 minus 2.67. It's going to be equals to, you have 20 times 2.67, so 20 times 2.67 plus you have the 0.4 times 20 times 10 times cosine 53.1. And then you have another here, 20 times 10 times sine 53.1. Okay, you just had to solve for M2, and you should get that M2 is, not sure, I think it's 36 kilogram. You have to check. I'm not sure. Okay, but this is the idea.